Okay, so to recall what we saw in the last class, we saw these furnaces, right? The two furnaces that we have in the syllabus. And the reason why we looked at the operations of these furnaces was because we're dealing with molten metal in casting. So we would want to know how are they melted, the methods of melting, right? And the limitations and advantages of each of them. Like cupola and crucible is what we saw, right? And even before, yes, we even saw core, right? Core baking, core finishing. Then we started with building furnaces. The factors responsible for selection of the furnace, right? But all the factors that we have that we can choose the different furnaces. And then the casting defects, the typical casting defects, right? So here are some of them we have seen. Let us quickly go through again. You have a blow, right? That is basically you're supposed to be having that continuation of the surface, but you have a void kind of what do you call error, right? A defect. So scar, right? Another one, blister, just as we have on our skins, right? And here scab, right? Gate, I'm sorry, what do you call the washing of the molding sand because of velocity, higher velocity through the gate, right? When the molding metal is flowing, the gate is supposed to provide proper channel to the mold cavity. A proper channel has to be provided for the mold cavity to enter into, I'm sorry, for the mold metal to flow into the mold cavity. But because of any other random reason, right, either the gating system is not good, that the molten metal has increased, the velocity of the molten metal increased, therefore it leads to this erosion of the sand, and therefore the molten metal would flow into that part of the soil which is eroded. So you call it wash away, right? Wash away of this mold, I'm sorry, sand mold. And this one, when you are not completely able to fill, right? Because of the reason I said, one possible reason could be the solidification has happened, right? Even before it reaches the last part of the mold cavity, this part of the molten metal is solidified. So that would be one reason. Another reason could be, even though it was not solidified, there was some other feature here which was not allowing it to go inside like that. So you have to take into account all these factors, that the design of the casting should be such that the molten metal can flow easily. The flowability of the molten metal should also be looked at, and the features, the casting that you're looking at, the different features of the casting should also be kept in mind. If there are any features which will not be able to fill, you can make them in a later step, like we do machining, right? Secondary process after casting. So that is for removal. For addition, you could weld it, right? If it is not possible because of these different reasons. And then cold shut, where you have multiple gates, right? And with these molten metal, they are supposed to join, right? Seamless joint has to be there, but they are not joined because of possible reason like this run, right? That they were not able to completely join. So proper fillets, etc., would what do you call, eradicate this kind of, or minimize this kind of defect, right? Hot tears, you have seen the last class, right? Here you see this is your what do you call, additional components, right? Screw, rubber, etc. But your casting, what was desired was this, and here you have a hot tear. This is because of shrinkage, or it could be because uh, the riser was not able to fill it right properly, and because of that shrinkage, this hot tear has happened, right? Or it could be even because of improper chills, right? We have not covered chills, right? We'll see that is there to achieve directional solidification. I had mentioned briefly, if you remember, that is there to give directional solidification, right? You see, I've included this slide just so you can understand, right? Better. You see porosity. You see that unable to completely fill, and you have those because of the escape of those gases. You have those holes, and that was not completely filled. It should have been filled by the riser. It's not filled. No holes, right? This is probably a spoke, right? Of a machine component, probably a flywheel or something. But point to be noted here is you have a blowhole. This is what you call a blowhole defect. And then mismatch, where you have cope and drag are not properly matched, as we have said, right? Aligning pins are used to align the cope and drag pattern. I'm sorry, cope and drag part of the casting. So if that is not there, then you will have this mismatch, right? That's not a desirable casting. Short core, just like your mismatch, right? It's not completely filled. Supposed to fill all throughout, but it has missed this part. Probably because the gating system was from here, started filling in here and there, but then when it came here, it had already solidified, right? This part of the casting had already solidified, and therefore the riser is unable to provide any more, or actually the gate is unable to provide any more material because it has solidified. So multiple gates, I believe, would solve this problem, right? A gate here as well, a gate there. So it depends on the size of the casting. We'll see a slide also where you have the reasons, the defects, and how do you avoid those defects. Inclusions, you see, inclusions are basically you have oxides, right? Formation of oxides, slag, etc. So that comes off as these dots, right? The original parent metal is this one, but the oxides, etc., because of oxidation or any other entrapment of gases, etc., reactions, you have inclusions. They are not desirable. They reduce the desired properties. The mechanical properties will change, right? That's not what we want, right? When we are calling this aluminum, right? When it was made of aluminum, and you have certain properties of aluminum that we know, but if these inclusions are there, they will act as stress concentration zones, and therefore that will be an what do you call a design failure, right? You cannot take this into account, so that is to be avoided. Inclusion is one kind of defect. Is it clear? What all we have seen? Casting defects. Okay. You see fusion. This is another kind of defect wherein the soil would, because of poor refractoriness of the sand, this molten metal, that soil would fuse into the molten metal. They'll mix, right? You are supposed to be this. What is supposed to be happening is the molten metal should solidify alone, but what is happening is it is solidifying along with the soil. The soil is having poor refractoriness because of higher temperature of the molten metal. The sand is also melting, and therefore they are forming a what do you call a mixed uh, composition. So that is not what we want, isn't it? You see here this part of the casting and this part of the casting. So the soil mixing is not a good thing. The bad refractoriness, the property of refractoriness should be properly maintained. The sand should be having proper refractoriness, and the older metal also should not be too high of a temperature, right? So you can avoid this kind of defect. You see here, inclusions, reasons for inclusions, you could have a faulty gating, a faulty pouring method, right? The way you pour the mold metal is also important. Inferior molding or coarse sand. Coarse sand is not good, right? Inferior quality. Soft ramming of mold. When you're ramming it, you're not ramming it properly. So soft ramming indicates the soil is not intact, right? The strength is not there, and therefore inclusions are bound to happen. Rough handling of mold and core. Even this is also another reason. If you are handling it roughly, then it is bound to have some disturbance, and therefore you would have this wash away of sand, isn't it? Or breakaway of sand from the mold cavity. What are the remedies? You could modify the gating system. You could improve the pouring to minimize turbulence, right? As I said, pouring is also to be taken into account. It should be so maintained that it is as laminar as possible to avoid this turbulence, and use of superior sand of, right? The possible remedies you can see. If it is an inferior molding of coarse sand, you could use a superior sand, right, of good strength. Soft ramming, you could provide a hard ramming, right, not too hard, so that escapement of gases would also be what do you call, restricted. The gases would not escape. And fusion, as I said, when you have that sand mixing with the molten metal. Reasons: low refractoriness in molding sand, faulty gating even is one reason. Too high pouring temperature of metal, as I was saying. Poor facing sand, this is also another reason. Facing sand, what we have seen in that video, right? They are sprinkled just so that we can have that easy removal of the pattern, right? And even the core, etc. So all these are remedies, right? You just do the opposite, right? You improve it or enhance it. If it is not possible to totally eradicate it, you try to minimize it, right? Or optimize it wherever necessary. Now, is that clear what we have discussed? If there are any doubts, you can ask regarding the casting defects. Okay. So you see, special casting processes. Now, apart from sand molding, what other processes do we have? The most general ones. First one being shell mold casting. Okay, as the name suggests, you have a mold that is almost like a shell, right? Thickness is quite less. That's what it sounds, right? That's what it looks like. And that's what it is. A shell mold casting or shell molding is a metal casting process in the manufacturing industry in which the mold is a thin, hardened shell of sand and thermostatic resin binder. So you have that shell made of sand and thermostatic resin binder, backed up by some other material. Now, just to look at the typical parts manufactured in industry using this shell mold casting process: cylinder heads, gears, bushings, connecting rods, camshafts, and valve bodies. All these are the parts, the general parts which are manufactured by this shell mold casting process. We'll see what the process is. You see, you have this pattern. Okay, a pattern is required. Okay, you have the pattern that is metallic pattern. Okay, metallic pattern, and you have heated it. You see, 350 Fahrenheit to 700 Fahrenheit. You have heated it, right? And you have placed it in a container, right? On the lid of the container. The container has what? It contains sand mixed with thermostatic resin binder, right? Sand mixed with thermostatic resin binder. Two things. Now you close this, right? This lid. So this is completely packed. Now this box can be what do you call, shaped, okay, or moved upside down, right? Just so that this pattern, metallic pattern which is heated, the sand and resin, thermostatic resin binder, that which comes into contact with the surface of this pattern, right? They will stick to it. The sand and the resin mixture will stick to this outer profile of the pattern because it is heated. The reason being, it is heated. You see, when it is again brought to this original position, you see that shell formation on that pattern. So the sand and resin binder mixture that has stick to the surface of that pattern. It has taken the contour of that pattern, and that's what we want. And that is a leftover sand mixed with a thermostatic resin binder, right, which is not stick to it. Now that was the third step. The fourth step is the shell and pattern are baked in oven to harden shell mold. So that's an oven, right? You are now trying to bake it. Why? To harden the shell mold, because although this was heated, the pattern was heated, but the shell is not so hard now. How do you make it hard? You bake it. Okay, so that there is proper uniform mixing, right? If at all there was some kind of zigzag mix composition, right, or this contour, that will now be proper because of that baking, right? Basically application of some heat. That's the fourth step. Now the fifth one is you remove that. You'll have some ejector pins, right? Not shown here, like this. You will have some ejector pins like this. So with the help of these, when you push them in this direction, these pins, this will help you to remove this shell. Okay, these are called ejector pins. Ejector pins. You will see this in that. Yes, we have even seen this earlier, right? In I believe some other process, right? Even this die casting, what we are going to see next, will also have these kind of ejector pins for easy removal of a component, right? Generally. So now, with the help of these ejector pins, you have removed this molding shell and you have the molding shell with you, right? This is the output from the fifth step. Now, what you're going to do is, that was just one half, right? You'll make another half, right? You'll join them together and you'll place them in a container with this backing material, right? You see, depends on the backing material changes, but it will be basically a supporting kind of element. It will support this shell structure, right? It is only there to support, because the molten metal you poured in, because of the metallostatic pressure, this backing material will support this shell, right? All throughout, as you can see, all throughout. When the molten metal is poured, it will support this backing material. That's what the purpose is. Now you see, I hope the process is clear. Any doubts? Okay, then. You see what are the properties and considerations of manufacturing by shell mold casting. The internal surface of the shell mold is very smooth and rigid, right? It has to be smooth and rigid because this internal surface, because the surface roughness of this will decide the surface roughness of the casting, right? Just as you have in sand mold casting, the cavity, the internal surface finish of the cavity decides the surface finish of the casting, right? So here also the internal surface, the surface finish of that internal surface will decide the surface finish of the casting. So it has to be very smooth and rigid because it has to withstand the molten metal temperature and metallostatic force, pressure, etc. Another point, shell mold casting enables the manufacture of complex parts with thin sections and smaller projections than green sand mold casting. So complex parts with thin sections, right? So we'll see another example where this point will be highlighted that complex parts with thin sections can also be made. Okay, it depends on how many shells you are making, right? You can even make thin sections. For example, you could make another what do you call shell, right? And you could pour metal in between those two shells. So that's how, right? Manufacturing the shell mold process also imparts high dimensional accuracy. Just to give you an idea, tolerances of 0.25 mm are also possible, right? This much tolerance is also possible. So dimensional accuracy is also there when it comes to shell mold casting. Further machining is usually unnecessary when casting by this process. So usually you will not do further machining because, as I said, after casting you do this secondary machining, right? Post processing, you can call it, just so that we can have certain surface finish and dimension control. But it is usually unnecessary when you are using this because it is having a high dimensional accuracy. That's why shell sand molds are less permeable than green sand molds. In binder, okay, and then green sand molds in binder may produce a large volume of gas as it contacts the molten metal being poured for the casting. For these reasons, shell mold should be well ventilated, right? So they are less permeable, and you have to maintain proper ventilation, right? Just so that we can have sound casting. Expense of shell mold casting is increased by the cost of the thermostatic resin binder, right? The cost of that resin binder is quite high, but decreased by the fact that only a small percentage of sand is used compared to other sand casting processes. So not much sand is required, right, as compared to other processes, as we have seen in sand mold casting or some other kinds. Shell mold casting processes are easily automated, right? If you want to impose some kind of automation, right, that is basically to use technology, right, for basically a program of instructions will be given, and you're trying to automate the process. So that can be done. This for the shell mold casting, it is possible to automate it. That is one possible, one good reason to go for shell mold casting. Where is that?
Class.
Okay. So the last point is manufacturing by shell casting may be economical for large batch production. So when you are having a large batch production, then this will be economical. Otherwise, it is a costly process, you can say, right? Now you see investment casting. As the name suggests, firstly, it is one of the oldest manufacturing processes. Yes, this has been there for quite a long time, dating back thousands of years, as you can see. In which mold metal is poured into an expendable ceramic mold. Okay, we'll see why it is called investment casting. The mold is formed by using a wax pattern, a disposable piece in the shape of the desired part. Okay, whatever part is it that your desired part is, okay, you're casting. So the wax pattern will also be made of the same shape, right? So the pattern is surrounded or invested into ceramic slurry that hardens into the mold, right? So when you are basically what this wax pattern will be dipped into a ceramic slurry, so that is basically surrounded or invested, right? That's why it's called investment casting. So this could be a possible question in the exam. You can say that why is it called investment casting? Because of this reason that it is the pattern what we are taking will be dipped into a ceramic slurry that will be completely surrounded. So it is basically invested, right? So that ceramic slurry, it hardens in the mold. Investment casting is often referred to as lost wax casting. Why? Because the wax pattern is melted out of the mold after it has been formed. Okay, we'll see the process. Okay, the wax will be melted out. That is why it is also called lost wax casting. However, since the mold is destroyed during the process, parts with complex geometries and intricate details can be created. Right? This is one significant advantage of this casting process, that very complex geometries and intricate details can be created, like jewelry, etc. Jewelry is made with investment casting. We have this complicated turbine blade, right, of jet planes and ships, etc. So all those blades, and even these what you call power plant turbines, etc. Those blades are also made with investment casting. You see, can make use of most metals, most commonly using aluminum alloys, bronze alloys, magnesium alloys, cast iron, stainless steel, tool steel. So almost all kind of metals can be investment cast. Okay, I mean they can be produced with investment casting. Okay, this process is beneficial for casting metals with high melting temperatures that cannot be molded in plaster or metal. Right, so high melting temperatures even. So you can go for this investment casting that which cannot be molded with plaster or metal. Okay, parts that are typically made by investment casting include those with complex geometry such as turbine blades or firearm components. Right, as I was saying, it requires the use of a metal die, wax, ceramic slurry, furnace, right, molten metal, and any machines needed for sandblasting, cutting, or grinding. The process steps include the following. We'll see the steps in the next slide. So all these are required. Okay. You see, these are the steps. Pattern creation. First thing, the wax patterns are to be made, typically injection molded. Okay, with the help of injection molding, you'll make these wax patterns, and these will have the exact dimensions and features, whatever is required in the casting. Okay, so the injection molded into a metal die and are formed as one piece, right? So in one piece, you will have all that setup, right? We'll see. Or should I show you the you see injection wax or a plastic pattern, right? This is the mold to make that pattern. Okay, injection molding as we were talking about, right? So you'll fill it, right? You'll fill this wax from here, and based on that shape of the die, this wax pattern will be created, right? You see the wax pattern, ejecting the pattern, the wax pattern is done. Now pattern assembly or tree. So you will make what you call a kind of a tree, right? Now you'll dip it in a slurry, right? Up and down, you see, dip it again and again just so it achieves a certain thickness, right? Stucco coating. We'll see what this coating consists of. And then you see the completed mold after repeated dipping, right, into the slurry. You have the completed mold. Now, because these were made of wax, you remember, these were made of wax. So once it is dipped and the wax patterns are inside, if you apply heat, that wax pattern will come out, isn't it? And all that is remaining is your shell, right? This coating. the slurry coating which was there, that will remain once you have applied some heat, right? If you have given some heat, the inside wax will melt out and the outside profile of because of that slurry coating will remain, and you will fill molten metal in it. As simple. And once that is done, once the molten metal is solidified, you shake out or try to break it. The shell, right? The outer shell. That we don't want the shell. We want the solidified casting inside, right? So you can remove them one by one, right? So you can have individual components. You see, this is the casting that we got, and this was a pattern, right? You see, the same features that you want in a casting, you'll keep in the pattern, right? That's how it goes. Is the process clear? Because we even have another diagram that will we can even look at that. But if you have any doubts so far, please ask. Okay, let's see these steps. Okay, as I was talking about, first step is the pattern creation. How you will create the pattern with material will be wax, right? Injection molded into a metal die, and you will form it as one piece, right? Pores may be used to form any internal features in the pattern. So there are internal features, you could use pores, just as we have done it in sand mold casting. So you will keep the pores inside that metal die, right? You'll keep the pores so that you can have the internal cavities if at all required. So basically, a pattern will be created, right? Pattern creation. Mold creation. How pattern tray will be dipped into a slurry of fine ceramic particles, right? The slurry will be made of ceramic particles, coated with more coarse particles, and then dried to form a ceramic shell, right? So that will be coarse particles, okay? Coated with coarse particles, and then they will be dried multiple times. Like you will dip it once, you will dry it. Again, you will dip it, you will dry it. So 3-4 times, depends on the thickness you are trying to achieve, right? And the what do you call the amount, the weight of the casting, because that weight of the casting will actually decide how much molded metal has to be inside and how much pressure it will exert on that coating. So that shell has to withstand that. So you will dry it multiple times, dip it, dry it like that. So you will have that shell around the pattern in the gating system. And then this process, as I said, is repeated until the shell is thick enough to withstand the molten metal it will encounter. Now you see the shell is then placed into an oven and the wax is melted out, right? In that oven, the heat will be given and the wax inside will melt out, leaving the hollow ceramic shell that acts as a one-piece mold, hence the name lost wax casting, right? Because that is melted out. This is the reason you call it lost wax. Now you'll pour it. Pour what? You'll pour the molten metal. The mold is preheated, right? Before pouring it, it will be preheated because you will have this difference of temperatures, right? That will lead to cracking of the shell, ceramic shell. So you will preheat the mold in a furnace to approximately 1000 degrees centigrade, and then the molten metal is poured from a dagon into the gating system of the mold, filling the mold cavity, right? Pouring of the molten metal. Cooling, right? Once it is solidified and cool, you see it depends on the thickness of the part, right? How much cooling time is to be given, the thickness of the mold and the material used, even because the temperature, the solidification time will depend on the material, right? Thermal conductivity, etc. So that will decide the cooling time.